So we have problem one, and we're going to just jump in and look at all these homework problems. So first of all, let's just begin by labeling letters. K, compression means X, mass is M. And the question is, we've got this spring with a spring constant, and we want to know the maximum speed it can give a 0.5 kilogram ball. So let's be clear on what we're given at the beginning. At the beginning, we're not moving. V is 0. So that means EK is 0. H is 0, and all of our energy is stored in the spring. What happens next is that we still don't have any gravity energy, no height. Once the spring is sprung, we don't have any energy, and we don't lose any energy to friction. So this means all of our elastic energy becomes kinetic energy. So we have EE equals EK. That's the equation that we set up from our bar graphs. And then what we can do after that is we can actually go ahead and use this to calculate the maximum speed that the ball acquires as it moves. So to this end, we can say 1/2 kx squared equals 1/2 mv squared. The halves actually cancel. So I have 850 times 0.4 squared is going to be 0.5 times v squared. And I'm going to do a little bit of math here, so don't be alarmed. This is 1700 times 0.16 equals v squared. Whoops, going to move that over a little bit. Being a little sassy there, aren't you? Aren't you, writing application? So that equals v squared. And so when we go ahead and solve for v, what we'll end up getting is about 16.5 meters per second. Now, if the spring is aimed so the ball shoots straight up in the air, neglecting air resistance, so no EE, we want to know how high the ball will rise. So we have all elastic energy. We start off with no speed and no height. And then the spring is sprung, so there's none of that, no air resistance. It's not moving at the top of its trajectory, it's still. So we end up getting EE equals EG, or if you prefer, 1/2 kx squared equals mgh. So we have 1/2 times 850 times 0.4 squared equals 0.5 times 10 times the height that we get to. So this ends up being 1/2 times 850 times 0.16 equals 5h. H is going to end up being 425 over 5 times 0.16. And when we simplify this out, H ends up being 13.6 meters. All right, so continuing here, we have the situation below where spring launches a roller coaster from cart from rest. Ooh, so that tells us we're at the bottom here. So we have no height and no speed. It's all elastic energy to start with. And then what ends up happening is we have this train at the top where it's got some kinetic and some gravity, no elastic, and no dissipated. So we're going to actually ignore friction because it says frictionless. So as we set this up, we're going to get EE equals EK plus EG. And so we want to know what the compression of the spring is. So we have 1/2 kx squared equals 1/2 mv squared plus mgh. And I'm going to go ahead and plug in my numbers just to see what we end up getting. So we end up getting 1/2 times 200 times x squared, which is what we're solving for. And that equals 1/2 times my mass, 0.25. I'm just going to rewrite that as a fraction. That's 1/4. So I'll write 1/4 there for m. times v squared, which is 16, plus 1/4 times 10 times the height, which is 1. Continuing on here, 100x squared equals 2 plus 2.5. So we end up getting x squared is 4.5 over 100. So x ends up being, when we solve, we're going to end up getting, it's going to be kind of an awkward number, 0.21 meters of compression. Now we have a similar situation in 4, where what we want to do is we have the speed at the top, which is only 3, and we have gravity, and we've lost when we're dissipated starting from all elastic energy. So let's use the numbers we had from before, but first we have EE equals EK plus EG plus E dissipated. So keeping this in mind, we need to kind of make sure we're combining things correctly. So let me just make sure of one small thing before we continue. So I'm going to go ahead and plug in here. So I have E elastic as 1/2 times 200 times 0.21 squared equals 1/2 times 0.25 times 3 squared plus 0.25 times 10 times the height of 1 plus the E dissipated, which is what I'm solving for. So continuing here, this is going to be about 4.5 equals 1.125 plus 2.5 plus E dissipated. And when we isolate E dissipated, we're going to end up getting again 1.125 plus 2.5 gives me 3.625. We add that to 4.5, and that's going to end up giving me 0.88 joules of dissipated energy. So that's it for the conservation of energy problems. I'm going to take a look at the next portion, the work energy problems, in the next set of videos.